Our body needs glucose, which comes from carbohydrates, to survive. The brain can only use energy that has come from glucose, yet the body can only store enough glucose to last for less than 2 hours. So what happens if you only eat meat for a day? What does the body do to prevent us from dying? It's through gluconeogenesis, which is a pathway used by the body to create glucose from other molecules. This is the pathway that prevents us from dying when we haven't had any bread, vegetables, or other carbohydrates for a few hours. The metabolic pathway, gluconeogenesis, is the synthesis of glucose from 3 and 4 carbon molecules, such as pyruvate. These molecules can be synthesized from some amino acids and triglycerides. The body will also use gluconeogenesis if too much of the glucose has been converted into pyruvate through glycolysis. This process can be reversed and turn the pyruvate back into glucose for storage or usage elsewhere in the body. Glycolysis is the process of converting glucose into energy. The body has 2 types of reactions, ones that build products, such as muscle or glucose, and ones that break products down. When products are being built, energy is required. When products are being broken down, energy is created. Glycolysis is one process that breaks products down, so it creates energy. Gluconeogenesis is the reverse of glycolysis with an extra step, which means it is a process that requires energy to be put into the reaction in order for it to occur. There are 9 steps and 1 substep in gluconeogenesis. Step 1. Pyruvate gets converted into phosphoenolpyruvate. This is the step that requires a substep in order for it to occur. When phosphoenolpyruvate is converted into pyruvate in glycolysis, a lot of energy is released, so doing the reverse is not energy favorable. This is why 2 steps are needed. The substep makes it so that less energy needs to be used. The first step adds a carbon dioxide into the pyruvate, forming oxaloacetate. By then removing the carbon dioxide, the energy is created to add the phosphate into the pyruvate and rearrange the double bond to form phosphoenolpyruvate. After the phosphoenolpyruvate is formed, the steps are similar to glycolysis but in the reverse. Most of these steps are just rearranging the previous compound. Step 2. Phosphoenolpyruvate rearranges into 2-phosphoglycerate. Step 3. 2-phosphoglycerate rearranges into 3-phosphoglycerate. Step number 4. 3-phosphoglycerate gets another phosphate added, forming 1,3-bisphosphoglycerate. Step number 5. 1,3-bisphosphoglycerate rearranges into glyceraldehyde. Step number 6. Glyceraldehyde combines with another 1,3-bisphosphoglycerate to form fructose 1,6-bisphosphate. Step number 7. Fructose 1,6-bisphosphate loses a phosphate and becomes fructose 6-phosphate. Step number 8. Fructose 6-phosphate rearranges to form glucose 6-phosphate. Step number 9. Glucose 6-phosphate loses the phosphate to form the final product, glucose. For most of these steps, the same enzymes are used to go in either direction, in glycolysis and gluconeogenesis. Step number 7, fructose 1,6-bisphosphate to fructose 6-phosphate, and step number 9, glucose 6-phosphate to glucose are the exceptions. Both of these steps require different enzymes than used for glycolysis. This is because in glycolysis, these steps actually require energy to occur, and so the same enzyme isn't needed when doing the reverse. After eating, the body immediately starts to break down the glucose into energy. However, if too much has been broken down into pyruvate, then the process will be reversed to change it back into glucose for storage. Remember, the brain needs this glucose energy as its sole source of energy, yet the body is only able to store a few hours worth of glucose. Once the body signals that it is getting low in glucose stores, it starts to turn protein into glucose. Fat and protein can be turned into oxaloacetate, one of the intermediates in gluconeogenesis. The oxaloacetate can then be converted into glucose. Fats can't be used as a source of glucose, In order for fat to be converted into oxaloacetate, a pyruvate is required. Since a pyruvate, which could have been turned into glucose, is required, the net glucose formed is 0. However, some amino acids, such as alanine and glutamine, do not require a pyruvate to create the oxaloacetate, so the net glucose generated is positive. When your body runs out of glucose, it starts using proteins to keep the brain running. You could potentially live off of no carbohydrates as long as you ate enough protein to keep your body functioning. However, if all your protein was being used to supply the brain with energy, then you wouldn't have the protein to build up muscles and keep them functioning like they should. Therefore, those who have no carbohydrates in their diet must eat extra protein to compensate. Gluconeogenesis is a pathway used by the body to create glucose from other molecules, and an important pathway that allows the body to store needed energy for the brain in the form of glucose. It is essentially glycolysis, which is the process of converting glucose into energy in reverse. There are 9 steps in the gluconeogenesis process. Step 1. Pyruvate gets converted into phosphoenolpyruvate. Step 2. Phosphoenolpyruvate rearranges into 2-phosphoglycerate. Step 3. 2-phosphoglycerate rearranges into 3-phosphoglycerate. Step number 4. 3-phosphoglycerate gets another phosphate added, forming 1,3-bisphosphoglycerate. Step number 5. 1,3-bisphosphoglycerate rearranges into glyceraldehyde. Step number 6. Glyceraldehyde combines with another 1,3-bisphosphoglycerate to form fructose 1,6-bisphosphate. Step 7. Fructose 1,6-bisphosphate loses a phosphate and becomes fructose 6-phosphate. Step 8. Fructose 6-phosphate rearranges to form glucose 6-phosphate. Step 9. Glucose 6-phosphate loses the phosphate to form the final product, glucose. However, a few steps are not energy favorable for reversal to different enzymes, steps 7 and 9, and added steps are included in order to overcome the energy differential. Pyruvate can be turned directly back into glucose, and some amino acids can also be used as a glucose store. In addition, protein can be used to create glucose storage. Ultimately, glucose is extremely important because it's the only energy source that our brains can use to survive.